Good afternoon, everybody. So Satish has a question of what exactly is the Monte Carlo method is. And what I'll try to do is to give a more general answer than the very specific Monte Carlo method that we have discussed. We have a lot of random processes in nature and decisions that depends on random input. And so it turns out that physicists makes use of the Monte Carlo method to analyze some phenomena sort of by brute force. So for example, if we wanted to know what would happen if somebody, let's say a terrorist, released a vial with some bacteria somewhere in a city, how it would propagate, we can derive the differential equation of diffusion and solve it deterministically. Instead, somebody can say, each bacterium can move with this probability to the right, to the left, with this velocity, and construct a process where they'll take a volume of air and assume some distribution of the motion of each bacterium and repeat it for 10 to the 9 bacteria that were released, and then watch what happens after a few hours. That is how they get distributed. Or if you want a scenario which is a bit more common, you have a new plant and you need to get permission because it releases some toxins into the atmosphere, and the city commission wants to know what can typically happen, so they have some random profiles of winds, and they will do a physical simulation each time with a different kind of wind. So this is the general Monte Carlo simulation. If you go to the website that I put on the Monte Carlo simulation, either one or both of those sources comes from physics professors, because they don't use the Monte Carlo simulation just for design like we do here, or for reliability calculation, but actually to model physical phenomena. What we are after in structural reliability calculation is to find the probability of failure of a structure. And what the Monte Carlo method basically says, you have some random parameters like geometry and material properties. Why don't you generate a very large number of structures and analyze each one of them? So that if, for example, you have a normally distributed failure stress, then for each structure you will go to a random number generator that generates normally distributed number and assign that failure stress according to that structure. The loads may follow some Weibull distribution, so you will generate those random loads, and each one of those structures we get some random loads, some random strength, some random geometry, and then you will calculate how many structures out of 1 million or 1 billion or 1 trillion failed, and you will calculate that way the probability of failure. Did I answer your question? Okay. Any other questions? Okay, so what we'll be doing today and next time is talk about things that are a bit closer to my heart, in that the reading material for today, which was on the refined Monte Carlo method, is based on a paper that one of my students, Ben Smarslock, is writing. And I put a short version of that paper that was submitted as an abstract. It will be presented in the next AIAA structures meeting. Next time, or if you go to the reading assignment from this file, you'll see that it's a paper by another one of my students, Palani Ramu, who gives sort of something between a survey and a tutorial on doing reliability-based design using two approaches, a direct approach and an inverse approach. And so today we are going to talk about what a textbook by Melcher that we found called the refined Monte Carlo method. I have a distrust of a method that call themselves refined, improved, new. The reason is that it gives you zero information. I think I said it last time. And so right now my tentative title for that is separable. And so I say that usually the limit state function of a structure, which is the structure that decides whether it's going to fail or not, can be written in terms of response versus capacity. G is equal to capacity minus response, and the capacity has to be larger than the response. And the capacity depends on one set of random variable or a vector R1, and the response depends on another vector. And let's say that the capacity is let's say that the capacity is the failure stress of the structure, and the response is the actual stress. If that's the case, could anybody tell me what could be maybe the R1 and R2, that is, what random variables will affect the capacity and what random variables will affect the response? That is, what random variable will affect the failure stress, what random variables will affect the actual stress?
Material properties for the failure stress.
Okay. It's not completely, it depends which material properties. For example, Young modulus and Poisson's ratio are going to affect the stress, while the failure stress itself can be viewed as random variable. But this is sort of dodging the question, in that you say the capacity is the random variable, the failure stress. But what actual randomness is responsible for the fact that the failure stress is random? That is, are there primitive variables behind that?
Process.
Yeah, so the processing is not likely to change much the stresses, but it's likely to have a large effect on the capacity. What variables have the strongest effect on the stress? What random variable have typically the strongest effect on the stress? Geometry and loading, right? That is, you take an airplane that flies, and if it's going to fail, and it's mostly due to the fact that, due to the response, then maybe the pilot did something unreasonable, and that is actually something that happened in the last Airbus disaster, or it was really caught in very turbulent air. Some airplanes had trouble because they flew behind a small jet flying behind a big one.
Geometry is not a random variable, right? The loading, it could be a random variable, but how come geometry is a random variable?
Okay, so the question is, how come geometry is a random variable? When the airplane is new, geometry is a random variable because every airplane is slightly different from another one, People said that cars, for example, that are built on Monday are quite different from cars that are built on Friday. Over time, the randomness increases because the part accumulates damage, and which changes its geometry. Oftentimes, when you investigate a disaster, you find out that there was such a huge crack that the area available for carrying the load was reduced by a factor of 10. We had a speaker here last year from the FAA, and he described an Alaska airline failure that was due to a screw that, because of poor maintenance, the thread were essentially 90% removed. So this is another source of randomness. Now, there are general methods for calculating reliability, and the Monte Carlo method is one of them. And if we are in a situation where R1 and R2 are different, so this is condition number 1, and condition number 2 is that when the failures typically correspond to only one of those two, that is the capacity or the response, being bad. That is, that you have failure due to a really shoddy construction, so that the capacity is very low or very high loads, but you can neglect the contribution of situation where both of them happen. Then this refined Monte Carlo, and as I said before, I'm still looking for a good name for the method. So maybe when we are done, can entertain suggestions. So let's talk about why I like to call it separability. So first of all, this is the picture. We have this curve that I'm showing here. Is it a PDF or a CDF for the response or capacity? It's PDF because it doesn't go to all CDF, ends up with 1 on the right side. So this is a normal response, a normal capacity. And failure is defined by the response being larger than the capacity. And what you can see is that the response, failure occurs more or less here. We don't need to worry about a good calculating contribution of the failure when both the capacity and the response are, let's see, the capacity being very low and the response very high. This is contribution from this little area that is almost negligible. Most of the action occurs here in the middle. So this is the one condition, and the other is that the response and the capacity are uncorrelated. This is not completely true for many structural problems, because if there is a shoddy construction, it can result in both poor material properties and poor geometry that may increase the stresses, but it's reasonably good. That is, and especially for the kind of data that we have on airplanes or cars or whatever, people certainly do the calculation. Now I try to formulate this condition of separability, and this is probably not the best, the most accurate way, but I like to think of it as the distance between the mean values being large compared to the sum of the standard deviations. So in this case, it's borderline. That is, the distance between the means is just slightly higher than the sum of the standard deviations. And the example that I'm going to show, I'm going to have also that condition. And the main reason that I'm going to show you an example where this condition is sort of borderline satisfied is that otherwise the probability of failure is very low. The refined Monte Carlo is indeed most useful when the probability of failure is very low, but I didn't want to sit in front of my screen and wait for Matlab to do billions of calculations, so I selected an example that I would get the answer right away.
So this plot says that if we have a structure with unusually low yield stress and unusually high stress, then we'll probably fail?
That's correct. That is, if you have a combination of unusually low yield stress and unusually high stress, it will fail. But what it also tells you is that you don't need both of them to happen together. So for example, if this is a place where, the middle of this interaction where the capacity is just slightly lower, one standard deviation below, and the response is just slightly higher, one standard. You don't need the extremes to happen simultaneously. Either one of them happens simultaneously and the other one is at the mean, more or less, or both of them are slightly bad.
How would this plot be different if you assume that response and capacity were correlated?
No. This doesn't tell you anything about the correlation. What will happen if the response and the capacity were correlated? It would mean, let's say that they were perfectly correlated. It would mean that you cannot have a situation where the response is high and the capacity is low. So for example, if they all depend on the quality of construction, and if you have a good structure, it will have low stresses and high capacity, and if you have bad structure, it's going to have high stresses and low capacity, then we cannot calculate the probability of failure by simply looking at, the area. There is a formula that takes into account the correlation. Okay, so just so we fixed, this is something that I mentioned before. So the response could be stress. I put the capacity allowable stress, and I tend to lapse into this error. It should be failure stress. Allowable is something that you use in design, and with a long tradition of working with deterministic method, I still lapse occasionally into calling the failure stress the allowable stress. So this could be a situation. You have a bar under tension. It has dimension T and W. It has a load P. And the load could be log normally distribution with a mean of 100 a standard deviation of 10. The failure stress may have a log normal distribution with 150 and 15. The width could be 1 with 1% coefficient of variation, 1% range with a uniform distribution. That means it will change between 0.99 and 1.01, and the thickness may change between 0.97 and 1.03. So this is a structure that has been designed with a safety factor of 1.5, because if you take the nominal values, that is the mean values, then the stress, the failure stress would be 1.5 times the stress. So aeronautical application may have something like that.
Wouldn't the sizing variables usually be a normal distribution?
Which variables?
Width and thickness? Like if you're specifying to all be 1 by 1.
Okay. So the question is whether the size variables like thickness and width would be normally distributed, and the answer is no. Normally distributed variable can go from -infinity to +infinity, and it's clear that if the dimensions are going to be grossly inaccurate, somebody will catch it. Okay, so even if you don't have strict quality control, you can count on the distribution being truncated. If you do have quality control, then there is somebody on the assembly line whose job it is to make sure that you build it to specification within a certain tolerance. It may be somebody at Boeing or at Ford or somebody at the FAA, and that truncates the distribution further. Finally, you could say there is probably a chance that the errors are going to be more toward the center than toward the ends. And so the distribution is probably going to look somewhere between normal distribution and a uniform distribution. But it turns out that the uniform distribution satisfies a mathematical nicety, which is the principle of maximum entropy or maximum ignorance. That is, if you don't know anything about a random variable except for the limit, the uniform distribution embodies the minimum amount of information that is, and it's in a sense sort of a worst case scenario. So when you are in the geometry specification where the engineer says, I want this dimension to be 1 inch plus or minus 0.01, you say, okay, that's the distribution that I'm going to assume uniform between those two. I'm sorry? It is conservative approximation, except, of course, then somebody can come and say, but there are cases where airplanes are not built to the tolerances. You know, there is a certain failure level in enforcing quality control. So, but within certain assumptions, it's a conservative approximation. Okay, now I'm going to show here a simple formula which is extremely important. So even though it's very simple, I'm going to spend quite a bit of time on it. It basically says if you are in a situation where failure is defined by capacity being smaller than the response, then you can calculate the probability of failure from this formula. It basically says the following. Take any value of the response, calculate the the PDF of the response at that value of the response, so this is the FR of R, multiply it by the CDF of the capacity at the same value of R, and integrate over the entire range of response values. So this is the formula. Any question about what this formula shows? I'm going to talk in a moment about why. It's sort of explained on the slide. But anybody has any problems if they had to program this integral?
Don't they take it a different way? The response takes in R1 and takes it in R2.
So let's say that the response, which is the stress, goes from 80 megapascal to 120 megapascal. So, and I have a distribution. For each value of the stress between 80 and 120, I'm going to calculate the probability density of the response. And if, for example, the stress is uniform between 80 and 120, then the F would simply be 1/40. Then I'm going to look for that value of the response, what is the CDF of the capacity, which is essentially, if the stress was, let's say, 85, what is the chance that it would fail? That is, the CDF of the capacity tells me the probability that the capacity is smaller than this 85. And so this goes to the meaning, why is this formula accurate? We take any value of the response, and we calculate what's the chance that the structure will fail with that value of the response. Because if you think about the CDF of the capacity, it looks like that. And if we take any value, the CDF is the chance that the capacity is smaller than that value. That's the definition of CDF. It's the area under the PDF. The CDF here is equal to this area. So what we have written here is take a value of the response, calculate the chance that the structure will fail with this value of the response, and then calculate the average of that. That is, so FC of R is the chance, is the probability that the structure will fail for a given value of the response. And we use the standard equation for calculating average. You have a function, you want to calculate its average. You multiply it by the probability distribution of the random variable. And so here, the random variable is only the response. For each value of the response, we don't treat the capacity as a random variable. We treat it as a lookup table. Given a value of the response, we know what the chance that the structure will fail because we know the CDF of the capacity. So this is a way of saying and this is a common situation in structural design. The response is very complicated. You need to run a huge finite element model in order to calculate it. The capacity is just, you have a failure stress of 120 megapascal plus or minus one standard deviation of, let's say, 5% with log normal distribution. So if somebody gives you a stress, you can immediately tell what is the chance that the structure will fail with that stress. So the capacity is often very simple. But even if it's not simple, we can often numerically generate the probability distribution function of the capacity independent of the stresses, because remember, we assume that the capacity is independent of the response. So we can do the calculation of FC on the side.
So would this give you a new probability distribution?
No, this just gives you a single scalar value.
Right, and if you did a series of those analyses, wouldn't it give you a new bell curve?
There is no possibility to repeat that. There is nothing that you can, you say if you do that several times, what can you change to do it more than once? This simply is a way of calculating the probability of failure from if you can generate the CDF of the capacity on the side. Now, there is nothing new about this equation. What happened is that Ben Smarslock had the task of looking importance sampling, which is a method that almost everybody tried to use in one form or another to reduce the burden of Monte Carlo simulation. And when he went to a textbook by Melcher, Melcher sort of in passing mentioned this method. And that ended up working better than the importance sampling. And to my amazement, even though it's a very simple method and it's particularly useful for structural analysis, in the 7 or 8 years that I've been doing structural reliability and going to conference on that, I haven't seen a single application of that method. So it's like a forgotten gem that for some reason people have neglected. Any questions about this one? Okay. Now, I wanted to call your attention in passing to a general way of generating in Matlab the probability distribution of a function if Matlab doesn't have the function available for you to do that, but if you have the CDF of the variable. And sometimes you will have the CDF from an analytical function, or sometimes you will have it from a large, that is, somebody did 200 tests, and you would want to do a Monte Carlo simulation enlarging these 200 tests to 1,000,000, and this is one of the ways you can do that. So if you want to generate the CDF of the response, you generate a random variable between 0 and 1. You go to the corresponding value on the CDF, and this is the random value of the response that you generate. So this is a general method if somebody gives you the CDF of a function to do a Monte Carlo simulation for that function. However, for the refined Monte Carlo or the separable Monte Carlo, what we are doing is sort of reverse direction. We generate a random value of the response, and we look up the CDF of the capacity. So this is just, and so the probability of failure, if you use the refined or separable Monte Carlo method, you will generate whatever numbers of RIs, responses, calculate the capacity, and then calculate the average. Remember, the formula that we used is nothing more than calculating the average of the CDF of the capacity. So the probability of failure can be thought as the average of the CDF of the capacity, average taken over the possible response values. So I'm going to have two sets of examples. This is the example that Ben invented, and it's a discrete example, so everything is crystal clear, except that because of its discrete, there are no integrals, and so it's not exactly the same, but the principle is maybe easy to illustrate. So let's say that you have a game where you have three marbles in a bag, and you are supposed to fish out one of them from the bag, put it back, fish another one, and you are going to lose if both of them are black. Okay? So what is the probability of failure? 1/9, right? And so we are going to see how we would calculate this 1/9 using the standard Monte Carlo method and the separable Monte Carlo method. Now, you can ask yourself, what's the analogy to response and capacity? So you can think about the first time you fish it as being the response, and the second part being the capacity, except that instead of one being larger than the other, failure happens when you have a black response and a black capacity. So you can think of it as having a really bad response and a really bad capacity. So this is the table of combinations. You can have only 9 possible combinations, and only one of them is black-black. And so the probability of failure is 1/9. If you started generating combinations like that with the standard Monte Carlo method, then you will get 0, which means non-failure for 8 of those 9 and 1 for the 9, which means that the minimum number of simulations that you can possibly use in order to find that 1/9 is 9 simulations. You need to be lucky so that in 9 simulations you'll get exactly 1/9, but there is no way you can do it in less than 9 and get the right answer. In the separable Monte Carlo method, you'll just fish one ball and calculate what's the probability of failure once you saw that first one. So if you saw a red one, you are done. You don't need to draw it the second time because you know that your probability of failure is 0. If you drew a blue one, again, you don't need to do the second one. Your probability of failure is 0. And if you drew a black one, you know that your probability of failure is 1/3. Essentially, you know the CDF of the second ball. And so conceivably, you can get the right answer by drawing only 3 balls. You know, if you did a red and a blue and a black, you did 3 trials and you got the right answer. That is, you calculate the average of 0, 0, and 1/3, and that average is 1/9. So this is the formula that says that with the standard Monte Carlo method, this is the best possible thing that can happen, while with the separable one, this is the best that can happen. And so instead of having a minimum of 9 simulations, you now have a minimum of 3 simulations. I didn't try to analyze what would be the error if you did 700 simulation on one and 700 simulation on the other. So this is just illustrative. And this next example that I'm going to do, I also don't do an error analysis. We don't have time to do that, but it's in the paper, and I'll expect you to read that. So I went to Matlab, and the advantage in Matlab is that I can have any number. And so I first used an example where I can get results that I can show on the screen every detail, but it doesn't satisfy the separability because I wanted to have a large probability of failure. And then I'm going to show you an example that has separability. So the first example is when the response has a mean value of 10 and a standard deviation of 1, and the capacity has a mean value of 11 and a standard deviation of 1. And the distance between the means is not small compared to the sum of the standard deviation. Actually, it's 1/2 of the sum. So this is just to show you the number. So this is the way I generated 20 instances of the response, and I similarly generated 20 instances of the capacity. And then I took the sign of the difference. Every time I have a 1 here, it means okay, -1 means failure. And so in order to calculate the probability, you have to do 20 minus the sum over 40. The reason that the 40 crops in is that every time you switch from success to failure, the sum changes by 2 and not by 1. That is, a 1 changes to a -1. And so this simulation told me that with the probability of failure is 0.3. And you can see that no matter how many times I will repeat it, with 20 simulations, I'll never get a number with more than 1 digit. So it's very crude. Here is how I would do the same thing with the separable Monte Carlo simulation. This time I limited myself only to 10 samples to show you that even with 10, I can get numbers that are not unreasonable. So I generated the response, and then for each value of the response, I calculated the CDF of the capacity, and these are the values. And basically what they say is that with 10.918, the probability of failure is 18%. You know, we are about 1 standard deviation from the mean, and so there is about 18% chance that you will be. With this one, the response is 9.1, so it's almost 2 standard deviation below the average capacity, and so the probability that you'll be there is only about 3.5%. Here it's 7%. With 8.5, you are 2.5 standard deviation away, and so your probability of failure is not even 1%. While with 11.75, you are 3/4 of a standard deviation above the mean capacity, and so your probability of failure is 77%. And so on. So this is just an illustration, but now let's look at accuracy. One way of assessing accuracy is simply to do repeatability. So I simply stacked those. First of all, I change the capacity to 13 from 10, so that the probability of failure will become small and will have a minimum level of separability. And I increase the number of Monte Carlo simulation to 1,000. And then I simply repeated all the operations that I showed you before. And here are 4 instances of the standard Monte Carlo method. And you see 0.15, 0.21, 0.019, 0.0120. First of all, we cannot get more than two digits. And second, you can see that the range is like almost a factor of 2 between the low and the high. Here is what we get with the refined Monte Carlo. 0.0169, 0.0186, 0.0156, 0.0158. If you calculate the exact answer, and one of the bonus problems is asking you to get this number, not by Monte Carlo, but by exact calculation, it happens to be about 0.0169. Any questions on this before we go to the bonus problems? Now, this is just illustrative. What's in the paper that I haven't got to cover is the equations that tell you what is the standard deviation in that. That is, for the standard Monte Carlo method, I've derived that. The paper shows it also for the separable Monte Carlo simulation for the simple case of uniformly distributed variables. And then it calculates what is the ratio between the number of simulations that you need to use using those two approaches.
So the main advantage of separable over regular is just the lesser number of times you have to.
Right. And this is very important. Like this morning, one of my students came to me. He's doing some Monte Carlo simulations, and he said it's going to run the entire weekend. Okay, so so it's not as if we are talking about, and he's doing a very easy problem. That is, that doesn't involve even finite element analysis. So. Okay, so problem number 1 is just to explain that this is to the logic. Why are we in the structural design community interested in the refined Monte Carlo, even though it's probably not very useful in other fields? And the second thing I would like I showed you a ball problem, and I showed you a numerical problem that doesn't have much physical basis, except that you think of it as stress and uniform stress. So in 2, I would like you to come up with any scenario that applies either to your research, to your life, whatever. Just come up with a nice example. And the third problem is to get this 0.016947 that I showed you there. I calculated it with Matlab with 2 lines. Okay, that is, I'm not saying that that's how you should calculate it, but this is it. Yes?
For the second part, do you want us to solve the problem or just set it up?
Well, I'm looking for the same level of illustrations that I had in the 2 examples that I have done. That is, have enough of a demonstration so that you can see that you gain something, even if you don't do 1,000,000 of them. So, yeah. Other questions? Okay, that would be all then.